Hi guys, let us discuss something about the sense organs in this class. So we have the ability to perceive different kinds of senses. For example, we have the skin, which has the ability of perceiving different kinds of senses like touch, pressure, pain, etc. Then we have the eyes, just actually concerned with the photoreception, that is light reception. Then we have the ears, concerned with the phonoreception, concerned with the hearing process. Then we do have the olfactory sense to perceive the sense of smell. And also we have just actually different types of taste we can perceive. That is what we have with reference to the tongue. So these are all the different types of sense organs. Now in this chapter, let us discuss something about the sensory reception and processing, particularly with reference to the eyes and ear. So I would like to start with something related to the photoreceptor structure in the body, namely the human eye. See, the human eye is located in the eye orbit. It is normally spherical in shape, and the movement of the eyeball is controlled by 6 muscles, innervated by the cranial nerves, for example number 3, number 4 and also number 6. Cranial nerves 4, just actually 3, 4 and 6 control the movements of the eyeball. So the movement of the eyeball is controlled by 6 muscles. For example, you have the superior rectus, inferior rectus, and then also the lateral rectus and also the oblique muscles, etc. Altogether 6 muscles. If these muscles are not properly actually working, if there is no coordination among these muscles, we have mainly the squint eye. So the improper coordination results in squint eye. Now in this chapter, let us discuss something about the structure of the eyeball and the photochemistry of retinal function, how far we can perceive the image on the retina, the nervous layer, that is a screen. So here, the wall of the eye, normally just you have 3 layers or tunics, or we can say simply the wall of the eyeball is composed of 3 layers or 3 coats or 3 tunics. The outermost layer is called as the fibrous layer, which is being composed of sclera and then cornea. The middle layer, what is called the vascular layer, which is composed of choroid, ciliary body and iris. And the innermost layer, nervous layer, which contains mainly the screen, what is called the retina. Now let us discuss the various components of different layers of the eyeball. I'll take first one, the outer fibrous coat. You can see it is normally white in color. It is a white layer of the eye. You can see it is white layer of the eye. It is the outermost layer. And normally it is thick and tough and made up of a dense non-vascular connective tissue. Dense non-vascular connective tissue or avascular connective tissue. And what is its function? This is a foam layer, very tough and thick. That's why it is a very foam layer. It provides shape to the eyeball as well as protecting the internal structure of the eye. What are the different parts of actually the fibrous coat? It is formed of 2 parts. One, the sclera, and the second one, cornea. Sclera and cornea. These are the 2 components of the outer fibrous coat. We'll see the various parts in the eye. That is a diagram later. I would like to go through first the theoretical part. So normally the sclera coat, it nearly covers about 5/6 of the eye. Out of the eyeball, 5/6 of the eyeball is well covered by sclera. It's normally white in color. You could see also an opaque image. And even you can see a small region of this layer as white of the eye. What we can see, the white color is nothing but the outer fibrous coat, namely the sclera. It forms a white of the eye. Just we can see only small portion of the white of the eye. Small portion of this what is called sclera as white of the eye. Now at the front side, the anterior part, we have this fibrous coat forms a transparent cornea. The transparent part of the sclera or the fibrous coat is called the cornea. It too normally non-vascular, but it becomes convex anteriorly. Just like what is called the sclera coat, it is also non-vascular, not supplied with the blood vessels, but it becomes convex anteriorly. And again it is made up of connective tissues. And the connective tissues normally containing the collagen fibers, elastic fibers, and also peptidoglycans, mucopolysaccharide, peptidoglycan. As in the case of bacterial cell wall, here too we have peptidoglycan, mucopolysaccharide. So the cornea is made up of connective tissue containing the white fiber, the collagen fiber. Then we have what is called the elastic fiber, nothing but the yellow fiber, and also the mucopolysaccharide peptidoglycan. So it is normally admitting the light is to enter into the eyeball as it is very transparent. Then lying over this cornea there is another transparent thin membrane, and this thin transparent membrane lying over the cornea, which is continued over the inner lining of the what is called the eyelid, is called conjunctiva. It's a transparent layer lying over the cornea, which is normally continued over the inner lining of the eyelid or the inner surface of the eyelids. So it is being formed of stratified epithelium. Unlike the cornea is formed of connective tissue, whereas its conjunctiva is formed of stratified epithelium. So this is about what we have with reference to the outer fibrous coat, which includes simply that is cornea, sclera along with the conjunctiva lying over the cornea. Now we have the vascular coat. So it forms a middle vascular coat. Normally it contains most of the blood vessels of the eyeball. And also it contains pigmented cells. The pigmented cells contain melanin. In the case of photophobia, as in case of albinism, one of the autosomal recessive disorder, where you have normally this coat, the vascular coat is non-pigmented, white in color, because of absence of melanin pigment, that results in photophobic condition, that is abnormally sensitive to light. People with some deficiency of melanin, in the case of albinism condition in the vascular coat, is unable to see the direct light, and this is because of the reflection of the light is within the eye. They are highly sensitive to light. That condition is called photophobic condition. So that is why we have this vascular coat should be pigmented. If there is a loss of pigmentation, then ultimately we have a disorder, albinism, that will lead to what is called the photophobic condition. The person is abnormally sensitive to light. Then what is the color of that one? So it contains most of the blood vessels. It contains melanin containing pigment cell. That is why it is normally dark in color when compared to the rest of the two layers, namely the outer fibrous, the inner nervous layer. Then it looks bluish in color. So that is because of the blood vessels and also the combination of the pigments melanin that gives blue color to this one. Now this part, namely the middle vascular coat, is differentiated into choroid, ciliary body and then iris. Mainly choroid, ciliary body or ciliary muscles we can say. Simply a collection of ciliary muscles together form the ciliary body. So choroid, ciliary body and iris together constitutes a vascular coat. Now about the choroid. I mentioned earlier, generally speaking in the vascular coat, the choroid coat is highly vascular and contains more pigment. That is why it is pigmented layer and highly vascular layer, which is normally found in association with the sclera, in close contact with the outer layer, namely the sclera. So highly vascular and highly pigmented in close association with the sclera. Now what is the function of that one? I mentioned earlier, if this layer is non-pigmented, then it prevents normally. It doesn't prevent the reflection of light is leading to photophobic condition. That is why the main function, it is comparable to the inner dark layer of the camera. The function of the dark layer of the camera to prevent the reflection of light is within the eye. The same function is also performed by this layer. It prevents the reflection of light rays within the eye as it contains melanin pigment as it is dark in color. And secondly, as it is supplied with more blood vessels, it nourishes the retina of the eye. So two important functions, preventing the reflection of light rays within the eye, and secondly, also it nourishes the retina of the eye as it is richly supplied with blood vessels. Now the ciliary body, the second part. So it is normally localized at the anterior part of what is called the choroid cord, or at the anterior part of the middle cord, the vascular cord. So anteriorly the choroid cord forms a thick ciliary body. This ciliary body is actually formed of a circular sheet of smooth muscles. Circular sheet of smooth muscles working involuntarily. And these muscles are called ciliary muscles. It is being formed of actually smooth muscles. They are arranged in what is called circular sheet, and that is normally smooth muscle, involuntary muscle, and such muscles are called ciliary muscles. There are two types of ciliary muscles, one circular and radial muscles. The contraction and relaxation of these muscles are responsible for changing the what is called the shape of the lens, because the lens is suspended to this ciliary body or the ciliary muscles by means of ligaments. The contraction of these muscles are responsible mainly for the accommodation of the eye, making a change in the convexity of the lens, because the eye lens is suspended to the eye muscles, namely the ciliary muscles, by means of what is called the ligaments, suspensory ligaments. So anyway, the ciliary muscles together form the ciliary body. There are two types of ciliary muscles. One is called the circular and radial muscles, the contraction and relaxation of which is responsible for changing what is called the convexity of the lens. So these muscles normally alter the shape of the lens or the convexity of the lens during the process of accommodation. So the process of accommodation is mainly by the suspensory ligaments and the ciliary muscles of the ciliary body. Now iris. See that one, it is again the anterior part of the vascular cord. And again it is a visible, we can see now it is a visible, colored and pigmented or colored visible part of the eye. Now this is the colored visible part of the eye. In the center only we have a small opening. So this part is called as the iris. This part is called as the iris. That's why it's called as, it is the anterior part of the vascular cord. Again it is a visible colored portion of the eye and a pigmented and opaque structure. It is opaque, not allowing the light rays to pass across. Again it is dark in color. This is because of the pigmentation. So this is the visible part, the colored part of what is called actually the eye region, and a pigmented also opaque structure. So pigmented and opaque structure and non-transparent structure. Now our eye color is because of the iris. Because the iris may be black in color or brown in color or blue in color. So different people have different iris color. Even in biometry, while for example we are taking for example while going for abroad, while taking for biometry analysis, for getting passport, even for getting Aadhaar and all other biometry analysis, they are taking what is called eye color, because the eye color is always constant for a particular species or particular individual in the case of human beings. So it may be black or it may be brown or it may be blue. So it is normally a contractile structure made up of again smooth muscles and then surrounding a small hole or opening. And that small hole or opening, for example, this is what is called the white of eye, and this is the iris part, and this opening is called as a pupil. This is what is called as a pupil. A small opening that is being surrounded by the iris muscles. And normally the people allows or admits the entry of light into the eyeball for focusing the light to be focused on the retina. So light enters only into the eyeball through this pupil. Now we have the muscles in the case of iris also, they are called iridial muscles. They are also circular and also that is what is called radial muscles. The contraction of these two muscles are responsible for altering the size of the pupil for admitting the light rays. For example, the diameter of the pupil has been just reduced when a person is exposing the eye to bright light. And similarly, the diameter of the pupil is normally increased when a person is entering into a dark room for admitting more lights. So, when we are in bright light, so normally the diameter of the pupil is adjusted according to the intensity of light. When the intensity of light is high in bright light, what will happen? Simply, just the diameter of the pupil is more. And when the intensity of light is less, the diameter of the pupil is more. When the intensity of light is more, ultimately the diameter of the pupil is less to allow only a small amount of light to enter. So, high intensity of light, normally small is the size of the pupil. The the diameter. Then low intensity of light, the diameter of the pupil is normally more admitting more light. So the size of the pupil has been altered according to the intensity of light by the iridial muscles. There are two types of iridial muscles as in the case of ciliary muscles. Here also we have radial muscles and then what is called circular muscles. Now the contraction of the radial muscles normally dilates the pupil of the eye. This is happening because of the sympathetic effect. The contraction of the radial muscles dilates the pupil of the eye according to the impulses of the signal from the sympathetic nervous system. The contraction of what is called the circular muscles normally constricts the pupil of the eye. That is, decreases the diameter of the pupil. This is because of the parasympathetic effect. So sympathetic nervous system dilates the pupil by making the contraction of the radial muscles, and the parasympathetic nervous system decreases or constricts the pupil by the contraction of what is called the circular muscles. The diameter of the pupil has been decreased. So this is the way normally the light intensity or the light rays entering into the eye has been limited according to the available light or according to the intensity of light. Now here is a picture just I want to show you. Now this is the outer white coat and this is what is called the choroid coat. The choroid coat is produced anteriorly in the form of a ciliary muscle. The ciliary muscle normally the lens is suspended to the ciliary muscles by means of ligaments. So the contraction and relaxation of the ciliary muscles alter the convexity of the lens according to the distance of the object seen, and that is called accommodation. And this is what is called the ciliary. This is called, I made a mistake, this is called the iris, made up of once again smooth muscles or iridial muscles. If there is a disorder, there is a dominant gene disorder. If the dominant gene undergoes mutation, there is a condition what is called aniridia. That is, the iris muscle is not fully developed because of the dominant gene disorder, particularly autosomal gene disorder. That disorder is because of dominant autosomal gene disorder, aniridia. This condition is called aniridia. A dominant autosomal gene disorder where there is no normal development of the iris muscles. So we have the middle coat is produced in the ciliary muscles and the iris. It leaves a small opening. This opening is called as the pupil of the eye. And this is the cornea. Now let's go further. Other structures. The same picture just I would like to give in a different manner. See, we have cornea once again, and then we have what is called this coat, outer coat, the sclera. Then the choroid coat being produced in the ciliary body, then iris. That is a vascular coat, consists of choroid coat, ciliary body and iris. The ciliary muscles are responsible for changing the convexity of the lens. The iris muscles are responsible for changing the size of the pupil, and it is working according to the intensity of light. These are the two structures mainly concerned with normally focusing the light rays on the retina, the innermost one. We'll come to this one once again later. Now this is another one. A picture the same one. Here also given the axis. Now this is a cornea. The light is being focused just opposite to the retina, a region what is called macula lutea. So here this is a macula lutea, that is called yellow spot, also called as just a centralis, area of centralis or area centralis, or yellow spot or macula lutea. We'll discuss later. Anyway, I'll show that one. This is a part of the retina just lying opposite to the pupil where the light is being focused directly, and this is what is called macula lutea, or also called as yellow spot, or just what is called just area centralis. And in that one, in the middle of the macula lutea, there is a thinned out portion of the retina, a point or a pit within this macula lutea present centrally. That part is called fovea centralis, where you have the visual acuity is greatest. Because this area is densely packed with the cones. So these are all some of the structures. We'll come back once again. I'll show you later. Now the nervous coat. we have to talk about the third layer, the nervous cord. Now this nervous cord again consists of non-vascular, highly sensitive to light or a photosensitive layer, what is called as the retina. So the nervous cord mainly consists of a photosensitive layer which is non-vascular in nature, where the image is being formed, highly sensitive to light, is called the retina. Now this retina is formed of three parts, or we can say three portions or three regions. One part is called as optic part, the major part which lies along with what is called the sclera. Then the part which is lying very close to the iris region is called as iridial part. It lies very close to the iris, it is in contact with the iris. And we have the ciliary part which lies in contact with the ciliary body. So the retinal coat, in one region, in major part, it is in contact with what is called the sclera, that is called the optic part, because the light will focus on that part. Other parts are, one, the ciliary part which is lying in close contact with the ciliary muscle, that is also a retinal part. Another part of the retina is nothing but iridial part which lies in close contact with the iris muscle. So that is about the three portions: optic part, ciliary part, iridial part. Now actually what do you mean by ora serrata? Ora serrata. Now if you are taking, actually we'll go back to the previous picture. See that one, this is what is called ora serrata. Ora serrata. So the ora serrata, in this region, what will happen? It is nothing but the circular margin of the optic part. Now normally after this one we have the optic part of the retina, and this part what we have the ciliary part. This is the ciliary part, and this is what is called iridial part. These are the three parts of the retina. So the optic part is in contact with the sclera. Then we have the ciliary part is in contact with what is called the ciliary body. The iridial part is in contact with iris. Now in the optic part, one region what is called ora serrata. What is ora serrata? So it is nothing but the circular margin of the optic part. This is a circular margin of the optic part which is continued over what is called the ciliary muscle. So you see that one which is continued over the ciliary muscle, and its margin is crenated or serrated, having a serrated margin like this, crenated margin, a serrated margin, a wavy-like margin, and that part is called ora serrata. It is nothing but a circular margin of the optic part, a region of retina, because we have three regions in the retina based on the position. Optic part, where the light is being focused mostly, it is in contact with what is called the choroid, it is in contact with the sclera. Then we have the ciliary part which is in contact with the ciliary body, iridial part which is in contact with what is called iridial muscle or iris. So anyway, ora serrata is nothing but the region of the optic part, a circular margin, whose margin are just actually the side part is serrated or crenated. Crenated means just like what is called saw-like structure. That is why the name is given as ora serrata. This is nothing but optic part of the retina. So now let us go further about what are the other components of the optic part. See, the optic part of the retina is differentiated once again into two regions or two parts. One part is the pigmented part, what is called pigmented retina. So this part is actually made up of cuboidal cells which contain dense or dark, that is melanin granules, dark melanin granules, nothing but the brown. So the outer pigmented part, so we have just normally the optic part, what I represented, has two regions. Outer pigmented part which is made up of cuboidal cells condensed with dark brown granules. The other part, the inner part, is called the nervous part. The inner part is a nervous part. It is also called a sensory part. And once again, it contains three layers from inside to outside. I will show that one. Now we have the three regions. If you are making a section of the optic part, and we have the nervous part I am taking here, I am showing you only the section of nervous layer of retina. From inside to outside, from inside outside. Now this is the inside region. I will show first one the entire. Now you see that one, this is inside part. This is inside part and this is the outside part. This is inside. So this nervous layer, namely what is called the sensory retina, is formed of three parts from just what is called inside to out. Now this is the inside region, this is outside region. So it is formed of actually three layers of cells. One, ganglion cells. This is a layer inside, starting from here towards outside. So this is ganglion cells. The inner nervous part, what is called sensory retina, is formed of three layers of cells mainly. Other cells also being formed, they are scattered. Now the ganglion cells from inside to outside. The next one, bipolar cells. This is the second layer. Then the third one, retinal epithelium, retinal pigmented epithelium. And before that, we have rods and cones cells. And this is not the third part of what is called the optic region. We have ganglion cells, that is the nervous part or sensory retina. We have the ganglion cells inside. Then the middle one, bipolar cells. The third one, what are called the photoreceptor cells like cones and rods. So starting from here outside. So first layer we have what is called, that is the ganglion cells. The middle layer, the bipolar, and then we have the photoreceptor cells of rods and cones, and the innermost one we have just the pigmented layer, that is not considered. So anyway, the nervous layer we are talking about. So I will show that one, the nervous layer. Now this is the nervous layer. Now this is the innermost region. So from inside to outside, from inside to outside. This is the outside region, just outer part of the eye. This is actually being faced towards the pupil inside. So the nervous layer, the sensory layer, consists of actually three types of cells. One, the ganglion layer made up of ganglion cells. Number two, bipolar cells having an axon and dendron. Number three, the photoreceptor cells. We have the photoreceptor cells, rods and cones. Now actually the nerve fibers of the ganglion cells together form the optic nerve, and this is the optic nerve leaving that one. Normally the light being focused on the ganglion cells and the action potential being generated normally in the bipolar cells by passing through the ganglion cells. We'll see later about. So anyway, we have the nervous layer is formed of three layers of cells, what is called the sensory retina. So inside ganglion cells, middle bipolar cells, and the innermost, that is actually we can say this is the outermost, just as per the diagram it is saying innermost, but actually this is the innermost and this is the middle one, this is the outermost, after which we have a pigmented epithelium, retinal pigmented epithelium. So this is a section of the nervous layer of the retina consisting of or showing the three different types of cells. Now again, once again the same picture in a different way. So this is outside, pigmented epithelium. Now once again, just I am taking this one, this is a whole layer, nervous layer of retina, inner limiting membrane. We have first one ganglion cell, and this is the outermost region, this is the innermost region, and this region is facing towards the pupil or facing towards the lens. And we have, that is the second one, bipolar cells. The third one, just what we have, the rods and cone cells, the photoreceptor cells. In addition to that one, we have scattered horizontal cells and also amacrine cells. Some cells are responsible for certain secretions. That is about the nature of the nervous layer. Now let's go to photoreceptors. So the photoreceptor layer, what we have just the outermost layer, from inside to outer, present nearly the pigmented epithelium, and it is being formed of two types of photoreceptor cells which are highly sensitive to light, and these are rods and cones based on the shape. Now what do you mean by rods? So these are all rod shaped actually cells, photosensitive cells, formed normally the outer position of the retina, and they contain light sensitive proteins called photopigments. Light sensitive proteins called photopigments. They are responsible. Both rods and cones are containing light sensitive pigments. Not only rods but also cones. We have the light sensitive pigments called photopigments. These light sensitive pigments are mainly formed of proteins, hence called light sensitive proteins, and they are simply called as pigmented proteins, hence called photopigments, as they are highly sensitive to light. Now let us take over the rods. In number there are about 120 million rods in the extrafoveal region. So fovea centralis is a region present in the midpoint of what is called area centralis, or yellow spot, and there you have more concentration of what is called the cones. So other than fovea, the remaining part of the retina are together called as what is called extrafoveal region. Extrafoveal region. So these are present in the the extrafoveal region, about 120 million. About 120. Now this part, actually this is what is called the fovea region, and these are all the regions other than fovea, what is called extrafoveal region. In these regions we have more number of rods, and in the fovea centralis, in the middle of what is called yellow spot, or we have more number of cones. That's why I mentioned rods are present in the extrafoveal region and cones are present in the foveal region. So the region other than fovea are called just extrafoveal region. So there are about 120 million rods are found in the extrafoveal region, and normally the rods contain a visual pigment, and that is normally purplish red in color, simply called as visual purple, and technically called rhodopsin. So the rods contain a purplish red pigment called rhodopsin and visual purple, and which contains what is called a derivative of vitamin A. That means it is a combination of protein opsin plus retinal. That is an aldehyde form of vitamin A. We'll see the chemical nature. It is being formed of the protein opsin plus retinal or retinin. That is nothing but an aldehyde form of vitamin A together form what is called the visual purple or rhodopsin. They are highly sensitive to light. Now here you see, based on the shape only, the photoreceptor cells are named as simply rods and cones. And normally the rods and cones are more or less actually unipolar neuron-like structures having many lamella, two regions, outer segment and inner segment. The inner segment contains normally the cell body and a branched synaptic terminal, which forms a synapse with the bipolar cells. And we have inside, we have lamella, and where you have just ionic channels are present. When depolarization in the membrane of the rods and cones occur, nerve impulse is being generated and conducted through this what is called synaptic terminal to the bipolar neuron, and then to the ganglion cells, and finally to the optic nerve. This is because of changes. So there is a potential difference occurs once they are exposed to the light, which creates what is called depolarization. Ultimately we have the formation of just the action potential, which is being just conducted through the ganglion cells via, that is the bipolar cells, to the optic nerve. So there is these are all the synaptic terminal. Now once again the arrangement of rods and cones, you can see the red color structures are cone like and the others are rods, and they are normally arranged towards the outer side. Now let's talk about what is the function of rods. Rods are responsible for seeing the object in dim light. That is what is called the twilight vision, also called as scotopic vision. So the seeing an object in dim light or twilight is called scotopic vision, and that is the main function of the rods. Then about the cones. There are 7 million cones. There are 7 million cones in contrast to the rods, because the rods are responsible for seeing an object in dim light. That is why they are more in number to perceive the light. But the cones are just we are seeing the object with the help of cones in the bright light. That is why the number of cones is less. So there are 120 million rods, now 7 million cones. And these actually cones are, I mentioned, already densely packed in the fovea centralis, a midpoint in the fovea or yellow spot or area centralis. And there are 3 different types of cones normally, with their own characteristic photopigments. There are 3 different types of actually cones. Each one has its own characteristic pigments for the perception of 3 different colors. One red or green. The third one just we have, that is what's called blue lights. So there are different types. There are 3 different types of cones with their own pigments. So there are three different types of pigments. For the perception of green, we have chlorolabe, L-A-B-E. For the perception of red, we have erythrolabe. For the perception of blue, we have what is called cyanolabe. So these are the three different types of pigments present in three different types of cones for the perception of three different colors. So cones are responsible for daylight vision or photopic vision and also responsible for color perception. That is a function. So rods are responsible for dim light vision and cones are responsible for bright light vision, otherwise called photopic vision, and also they can perceive the colors. So we have the different colors. The sensation of different colors produced due to the various combinations of cones and their pigments. So we can produce different colors, mixture of red, blue and green. So the sensation of different colors are produced because of the different combinations of cones and their pigments. When all these actually cones are stimulated equally, a sensation of white color is produced. If all the cones are stimulated actually equally, we can have only white color. A sensation of white color is normally produced. A sensation of white color is produced only when all these three pigments have been stimulated equally. All these three cones having the three different types of pigments are just stimulated equally. But it is not so in most cases. So we have normally the different sensations are produced because of the different combinations of cones so that we can perceive the different colors. Now I mentioned already what do you mean by yellow spot or macula lutea or area centralis. Now this is the region which is yellow pigment, that is why it is called yellow spot, present in the retina just exactly opposite the pupil, exactly opposite the pupil, and also lying very close to the blind spot or lateral to the blind spot. So it is nothing but yellow spot. This is because of yellow in color and also called fovea centralis or area centralis. Macula lutea or fovea centralis. Sorry, I made a mistake. Macula lutea or area centralis, and it is a yellow part which is normally present just opposite what is called the pupil. It is nothing but a part of the retina and also lying very lateral to the blind spot. Now in the middle, what is fovea centralis? It is a central pit or a central part, a shallow region formed in the fovea or yellow spot, or we can say in the yellow spot or macula lutea, or we can have for example area centralis. So fovea is nothing but a part of the yellow spot or macula lutea or area centralis. It is normally just actually thinned out portion of the retina, thinned out portion, just a slight cavity, a pit, thinned out portion of the retina, where you have more number of cones closely packed. So which contains densely packed cones. That is why this region has more acuity. So when it is a point normal where you have more acuity or visual acuity is there, that is the highest resolution is there, and that is why this part is considered the most important part where the image is being formed sharply. This is because of the accumulation of cones. So it is a point where visual acuity is normally the greatest. Visual acuity means the resolution, having high resolution power in this region. So visual acuity is always greatest in the area centralis, blind spot. And normally in the retina region, in one spot the optic nerves leaves from the eyeball at the posterior end, and the retinal capillaries or the retinal artery normally enters into the eyeball, and that spot is called the optic disc. So optic disc is a region where the optic nerve leaves the eyeball and what is called the retinal arteries enter into the eyeball. As this region is normally devoid of the photoreceptor cells, without photoreceptor cells, this area is unable to perceive the images, hence called as a blind spot. So blind spot is nothing but the optic disc region where the optic nerve leaves and the retinal arteries or the blood vessels enter, where there are no rods and cones. That is why there is no perception of images at this point, hence called that is blind spot. Now the lens. So it is a biconvex transparent structure, you know that one, just placed behind the iris. It is made up of long columnar epithelial cells, hence called lens fibers. The columnar epithelial cells which are elongated is called lens fibers. So it is made up of long columnar epithelial cells called lens fibers. The lens fibers normally have an accumulation of proteins. The name of the protein is called crystalline. The name of the protein is called crystalline, which is made up of what is called elastin protein. See, the lens fibers, namely the epithelial cells, contain or have an accumulation of proteins called crystalline. That crystalline in its turn is made up of what is called elastin protein. The entire lens is covered or ensheathed by what is called lens capsule, and the lens is suspended to the what is called the ciliary body by suspensory ligaments. So the contour of the lens, the convexity of the lens, the shape of the lens is altered because the lens is connected to the ciliary muscles by means of suspensory ligaments. Now what is accommodation? So human eye has a lens apparatus whose convexity can be changed for near and distant objects. Suppose for example when a person is seeing a near object, it becomes more convex. That is, its refractive power has been increased. When a person is seeing a distant object, then the convexity of the lens has been decreased. It becomes more flat. So this adjustment of the lens according to the distance of the object seen is called accommodation. So we have a lens apparatus whose convexity can be adjusted for focusing near and distant objects. Such ability of the lens to focus objects at varying distances is called accommodation. The accommodation is mainly brought about by ciliary body, namely the ciliary muscles, along with the ligaments, namely the suspensory ligaments. These are the two structures mainly responsible for bringing about the accommodation of the lens according to the distance of the object seen. Now what are the compartments of the eyeball? So if you are taking the eyeball, there are two compartments. One compartment is called the anterior compartment. Another one is called as a posterior compartment. The anterior compartment is normally small in size and the posterior compartment is larger in size. Again, the anterior compartment being divided into two chambers. One is called anterior chamber, the one which is being present between the cornea and iris, and a posterior chamber, the one which lies between the iris and the lens. Now the anterior compartment, that is the anterior and posterior chambers, have been filled with what is called a thin watery fluid called aqueous humor, and that is responsible for maintaining the intraocular pressure. Now about the posterior compartment. The posterior compartment is normally large, which lies behind the lens or between the lens and the retina. Now this posterior compartment contains again a transparent jelly-like vitreous humor, and this vitreous humor is made up of a gelatinous protein, though it is jelly-like but it is transparent. Now what are the other structures related to? Some accessory structures related to the eye. Now the ciliary glands. These are all modified sweat glands which open into the follicles of the eyelashes. Their main function is lubricating the eyelashes. So ciliary glands, nothing but modified sweat glands which open into the follicles of the eyelashes, and they secrete some fluid for the lubrication. The second one, meibomian glands. These are all special modified sebaceous glands present at the rim of the eyelid region on the inner side of the eyelid, at the rim of the eyelids, inside or the inner side. And these glands secrete an oily fluid what is called meibum, and that one prevents the evaporation of what is called the eye's tear film. So we have the tear, a thin layer of water lying over the conjunctiva. This is what is called tear film. That one is responsible for the normal vision, and that one's evaporation is being prevented by what is called this meibum, which prevents the evaporation of the eye's tear film, a thin layer of tears lying over the conjunctiva. Now the lacrimal or tear glands. These glands are responsible for the secretion of the tear, which are normally situated in the suprolateral corner of the suprolateral corner. This is a supralateral corner of the what is called the eye orbit. Supralateral corner of the eye orbit, concerned with the secretion of. Now the mechanism of vision or photochemistry of retinal function. So we can see the objects both in what is called dim light as well as in bright light. Seeing an object in bright light, dim light, seeing an object in dim light is called scotopic vision. So, seeing an object in dim light is called scotopic vision. I mentioned already there are about 120 million rods which contain the photosensitive pigment, what are called the rhodopsin or visual purple. It is nothing but actually a combination of retinine. It is also called retinal, an aldehyde form of vitamin A, the rhodopsin, plus a protein part, commonly called as opsin, specifically called scotopsin, because it is concerned with the scotopic vision, seeing an object in dim light. So it is a combination of a protein opsin, specifically called scotopsin, and aldehyde form of vitamin A called retinine or retinal. So what will happen normally? So when actually the rods are extremely sensitive to light and are responsible for seeing an object in dim light, and this type of vision is called scotopic vision. I mentioned earlier what is happening during the perception of light by the rods. When the light is falling on rhodopsin of the rods, it is being bleached. The meaning for that one, it's being broken into its components, namely retinine and scotopsin. As a result of that, what will happen? Which reaction, the bleaching, causes a change in ionic composition inside rod. That is just like that one, potassium and sodium, as in the case of conduction now impulses. Due to changes on this ionic composition because of the permeability of the membrane, the depolarization of the rod membrane takes place, which results in the development of impulse, and that is being conducted all along the nerve fiber. So this is the same way as we have the formation of nerve impulse by means of depolarization or action potential in the nerve fiber. So ionic composition changes, then we have the permeability. This is because of the permeability to sodium and potassium ions that leads to depolarization, as in the case of nerve fiber, that results in the formation of nerve impulses which is being transmitted all along the nerve fiber. Now, photopic vision. So seeing an object in bright light is called photopic vision, and that is a function of what is called the cones. And as in the case of rods, cones also formed of pigments. The pigment is made up of opsin, here it is called photopsin, along with retinine. And normally there are three different types of pigments, what I mentioned, the cones, each one responding to different wavelength for red, green and blue. I mentioned erythrolate, cyanolate, and also just we have for green chlorolate. So the color vision is the function of bright light vision, and cones are responsible for the perception of colors. A person would see the color only in bright light. So a bright light, just normally the color vision is the function of bright light vision, and cones are responsible for the perception of colors. A person can see only the colors in bright light. In dim light or in dark, he can see all the colors as gray. Then cones function in bright light vision, I mentioned already. The system has more acuity. The system has more acuity, can have more resolution. Then the system has more acuity, that is actually the acuity power has been greatest, more resolution, and can perceive colors. This is what is called bright light vision or what is called photopic vision. This is nothing but the cone's function, which functions in bright light, which can perceive the colors also. The system has more acuity only in bright light. This is called photopic vision or bright light vision. So I will come to the last part. Just I will go through what is happening, what is the mechanism of photochemistry of retinal function. So we have light rays in visible length. They are being focused on the retina by means of cornea. Then we have the lens and other fluids. Now these light rays fall on the photoreceptor cells, maybe the rods and cones. As a result, the bleaching of the rods and cones pigments taking place, and that is called breaking up of light sensitive pigments of rods and cones. So the pigments are light sensitive, either the rhodopsin or the different types of pigments of the cones. They are being broken or being bleached because they are highly sensitive to light. And as a result, we have changes in the chemical or molecular structure of the opsin protein. Changes in the molecular structure of the opsin protein. So we see that one, the light being fallen, it's being focused, and ultimately we have what we have just the generation of action potential in the ganglion cells just through the bipolar cells. Now this is the pigmented layer outside. We have rods and cones also here. We have the bipolar cells, and this is the ganglion cell, and this is what is called the optic nerve. All the nerves joined together, leaving at the optic disc as optic nerve. I'll come to the last part. Now this is the last part. So as normally changes in the structure of opsip occurs because of the breaking down of or the bleaching of the pigments of the rods and cones, and the permeability of the membrane changes. The permeability of the membrane changes means with reference to the rods and cones, with reference to what is called sodium and potassium ions, and as a result, generation of potential difference occurs in the photoreceptor cells. This is because of the change in permeability for sodium and potassium. So generation of potential differences in the photoreceptor cells, rods and cones, and which leads to the generation of action potentials in the rods and cones, which is called the impulse. And these generation potential or action potential have been generated in the ganglion cells also through the bipolar cells. And finally, now the transmission of action potential happens to occur through the optic nerve to the visual cortex of the cerebrum, namely the occipital lobe, where the interpretation occurs so that the person can see an object. So the main idea, as in the case of for, that is a transmission of impulses in a normal nerve fiber, generation of action potential because of ionic change. The ionic channels have been generated, ionic channels have been opened for sodium and potassium according to just what is called the stimulus given. So likewise also here the membrane permeability of the rods and cones, and then we have the generation of potential difference in the rods and cones, and followed with the action potential generation that is being normally conducted through the bipolar cells to the ganglion cells and ultimately reaching the optic nerve, and that one conducts the impulses to the visual cortex of the cerebrum where interpretation occurs so that a person can see all that is actually the different colors. This is what is happening. The image is being formed on the retina, which is acting as screen, and we can perceive the different the images what we can perceive through the reflection of the light is from an object being focused by the lens and the structures on the retina, then being stimulated where you have the photoreceptor cells. Ultimately they generate action potential, and finally it is being transmitted as an impulse. So with this I conclude just one part of what is called the sensory reception processing with reference to the nature of the eye and its functions. Let us see about the structure and functions of the ear in the next class. Okay, thank you. Till then.